jah. Mida? Korda? Ma natuke tegin ka veel. No seal mõned nurgad olid. Üldiselt oli sul kenasti. Aga ma tegin, et emme midagi narida ei olnud, mis ma katsusin kõik nurgad ära teha. Praegu hakkangi. Jah. No ma ei tea, ma arvan, et võib-olla lähevad järgmiseks korraks. Ma arvan, et see on nüüd vaiad tuleb sisse taguda. Ma arvan, et Emmi elab üle, kui järgmine korda läheb. Praegu tal oli esmane soov oli need niitmine ikkagi. Me saame halva ilma taha ka pugeda. Hello everyone, how are you? How are you? Yeah, someone is asking if it's well, with some we were asking what was the force needed to pull, not what is the coefficient of friction. I think you got a little bit question incorrectly. But so I have got email from Hussein with answer. What about the rest? Did any one of you still got, apart from Hussein, some result? No? Can you hear me? Tell me if you can hear me, because somehow I haven't from any.
Yes, we can hear you, Mr.
Okay, very good. Then, so tell me if you try this problem at home.
Yes, I tried it, but I didn't get like a final answer.
Okay. All right. Okay, just. So let us start solving it. And well, to be honest, this problem is not too easy because, well, actually, yes, I gave you a recommendation, but there is a small trick which you, or some small thing which you probably won't notice. And the thing is that I told you that work done is something like coefficient of friction multiplied by n multiplied by the slipping distance. But the thing is that actually, what is the question is, what is this n here, normal force, because n is not mg divided by 2, but slightly different. So if we want to do it correctly, then we need to calculate exactly what is n. Now, let us do it first in a little bit incorrect way. Like I think Hussein assumes that n is mg over 2. Is that right, Hussein? Are you there? Hussein? For some reason, I don't think I can see Hussein right now here. Anyway, so.
He just joined.
Sorry? Okay. Yeah. Hussein? So you solved this at home, but I guess you assume that n is mg divided by 2. Is that right? The thing is that actually it is not. And now, can you see a reason why n is not mg over 2? Well, if this thing here were resting at horizontal planes, then of course n would be mg over 2. But as soon as we apply here horizontal force at this height here, we are going to apply.
Maybe because of the tension force.
We kind of press more on front row wheel rather than back wheel. If you push it something, it will more like you're trying to overturn it, and so because of that, it is trying to get more support from the front rather than from the back. So more formally, you can say that if you consider force balance with respect to this point here, so gravity force does not go here into play now because arm of gravity force is 0, and then we have torque due to F, which is F times R, which turns there, but then we have this is compensated also, well, it is also turning on that way the torque due to normal force here. Torque due to friction force does not go into play because it has 0 arm. It goes through this line here, but normal force does have. So if we have here N1 and here we have N2, then FR and N1 turns both clockwise and N2 turns counterclockwise. So we add here N1R and all this equal to N2R. And then we can see that N2 minus N1 equals F. So N2 and N1 are no longer equal to each other. Okay. So then,
Mister, I have a question.
yes.
What about the tension force? Why didn't we count it while counting the torque?
Tension force, you mean here is a rod or things like that in the chain?
Yes, that's what I mean.
The thing is that I consider the whole thing as a total closed system. So I am not considering like the force from one part of the thing to the other part, but also torques, external torques. And so these are change and tensions. They are internal torques, and due to Newton's third law, two parts cancel out from each other. So we need to consider only external forces, external torques, and this we have N1, N2, and gravity and frictions. That's all we have.
What's the F in the equation on the top left?
Sorry?
The F in the equation you wrote.
Oh, this is the external force which we apply here. We push it in that way, applying it into the middle.
And how is it R? What's...
Because the radius of the wheel is R capital. And if we apply it here and consider torque with respect to this point here, so the arm is R.
Oh, yeah, okay.
Mm-hmm. Now, on the other hand, of course, N1 plus N2 equals mg, because this is external force down is mg, and the external force up is N1 plus N2. So from here we obtain that N1 equals mg over 2 minus f over 2, and N2 equals mg plus f. It's the other way around. N2 is N2 is bigger. N2 is bigger. And N2 is mg plus f divided by 2. So you can see that N1 plus N2 gives mg, and N2 minus N1 gives f. Now we have expression for N1 and N2 in terms of f. And then we need to figure out which wheel starts slipping and which wheel is rolling poorly. So now where the friction force might be bigger. Friction force, where we need bigger friction force to keep it rolling. Let us see. So, do you have idea?
Why did you say the sum of torques is 0?
What is 0? Torque of my pivot point is here. So everything, all the forces which go through it have 0 arm and contribute 0 torque. So one of those is gravity force, which is applied to the center because center of mass is at the center. And then we have a friction force, this horizontal goes also through this point.
Okay.
Yeah. And so I will, if I apply here torque, let us say, to this, we try to turn this wheel with certain torque M. Then a tension force here, which compensates that, is inversely proportional to the radius of the cogwheel. So I would say that with the same tension of the cogwheel, torque here is bigger because tension in the cogwheel, in the chain gives a bigger torque here because arm is bigger rather than here. So this is being turned with a bigger torque than that, and so this would probably start first slipping. We can later check this assumption, but I would say that this starts slipping. So let us assume that here is slipping. All right. Did you follow my motivation? Why I believe here it starts slipping first?
Because it's the radius is bigger, right?
Yeah, because here cogwheel is bigger with the same tension force here in the chain. This gives bigger torque to here rather than here. because here a torque is arm, which is A multiplied by tension force. Here is multiplied by 3A. So this is 3 times bigger torque than here, applied from the chain to the wheel. And so we turn it more with a bigger torque, and so probably it will start because of that slipping. And then let us say that this thing now our approach was to apply the virtual displacement method and calculate the force balance. So suppose this thing here moves to the distance 6, and then we make work W equals F times X on the one hand. On the other hand, this goes to the energy loss here, because if we push it slowly, there is no change of energy anywhere, but we have certain energy loss here. We don't have here because here is rolling, no slipping, but we do have here. And now suppose, let us try to imagine how much we have slipping here if we roll here to a certain distance 6. If we roll here to a certain distance x, then angular rotation here is x divided by r. And but each time we move this chain relative to the cogwheel to a certain distance, this rolls here, rotation here is 3 times smaller. Which, okay, let us do it properly. So here, displacement of the chain relative to the wheels in that case is omega y equals omega multiplied by A. Okay, and here we have also same formula, but here we have different angular speed, omega prime. So here y is the same y, which is now omega prime times 3a equals omega times a. So omega prime is 3 times smaller than omega. Omega prime, from here we go.
What's y?
Sorry?
What's y?
Y is how much the chain is displacing relative to the cogwheels. If we roll here by x, wheel rotates by omega equals x times r. Now cogwheel is fixed to the wheel. Cogwheel also rotates as much. Now if cogwheel rotates at rate omega, I would probably to be better not omega, but it is not angular speed, but it is the angular rotation. Right here,
Okay.
angle phi, yes. So angle phi by which it rotates is 6 divided by r, and then y, how much the chain rotates, is the angular rotation of this cogwheel multiplied by the radius of the cogwheel, which is a. And now y is how much chain is displacing relative to the cogwheel here and here. But here the radius of the cogwheel is 3a. So if we had here rotation by angle phi, here we have rotation by angle phi prime. Here y equals phi prime multiplied by 3a on the one hand, but on the other hand we know this is phi times a. So we know that now the rotation angle is here is a phi prime equals phi divided by 3. So 3 times smaller angular rotation at this wheel here. Okay.
So now it's not faster as we assumed at the beginning.
No, we are not speaking about how fast or slow it is, but the question is how much it slips. It doesn't matter which direction it slips, but the main thing is it does slip. So we displaced here by distance 6, but this here surface of this wheel here, it displaces now by x prime equal to phi prime multiplied by r. and this is because phi is 3 times smaller, then this is phi r divided by 3, and this is now x divided by 3. So if we rolled by distance 6, the surface of the wheel relative to this vehicle here turns by 3 times smaller, only by x divided by 3. So the slipping distance is the difference between those two. It slips by delta x equals 2x divided by 3. Is this more or less okay?
Wait, what is delta x?
What is delta x?
Delta x.
What is
Yes.
delta x? So delta x is how much this wheel slips relative to the ground. So what happens here is that what we do here, we mark here on this wheel a certain point, which is at contact now. Right now, right now this is contact, and we mark on the ground also point. And now we displace the vehicle by distance 6. If we take displaced by distance 6, so this contact point of the vehicle, it used to be here. The contact point with the vehicle used to be here, but now contact point is here at the distance 6 because the vehicle displaced. But the wheel rolls, and now this point here is at distance x over 3 rotated by x over 3. So it was here, but now it rotated to here, which is like 1/3 of this displacement here. And so we have now because so the point which is now in contact, the point of the wheel which is now in contact with the ground, because it rotated now by so that surface points of the wheel displaced by x over 3. So now the point which is contact with the ground is this one here. And but the vehicle itself is displaced by x, so that the point of ground weight is at constant is here. I'm not, well, it's not so easy to explain it, but probably I should try to make a little bit better drawing here to explain what happens. So let me try to here at the bottom here another drawing to explain.
Okay.
So,
No problem.
So we have here wheel at the beginning, and then next position here. This is initial position. Now next position is let us do it in red now. Is displaced everything by x. Now these are the new positions of the wheels. Okay. And so now if we draw here ground, if we draw here now ground, it's not very convenient for me to draw this here. Now the red circle was not too, it went too low. Okay, so now if the contact point at the beginning was here of the first wheel and of the second wheel was here. The new position of the contact point is both is displaced by x, by same amount. So it was old contact point and new contact point. Now, let us mark a point on the wheel which was in contact previously. Previously on this wheel, the point which was contact is this one here. But now the wheel rotated and it went up. So basically it is still at the same place here because it just rotated and lowest point when it's rolling, the lowest point don't slip. So it just went a little bit up, but it's also almost at the same point where it was before. Because this rotated by angle, which is phi is x divided by r. Okay, so angle which rotation which x divided by r, it went up, but because of slipping, it's just above the marked point before. So the marked point which was on the ground, the previous contact point of the wheel was ground, and the corresponding mark which we made on the wheel is now slightly up. But what happens here? What happens here is that the contact point here of the wheel is here, but the angle of rotation is 3 times smaller. And so the marked point on this wheel here is now here. Okay, and previously the marked point was about this blue line, similarly to here, but now it is here. So it slipped here now, the distance 2/3 of x. If from here to here is x, and from here to here is 1/3 of x, so the slipping distance was 2/3 of x. Is this more or less clear what is happening? With some, yeah.
Shouldn't pi be x over 2 pi r?
Phi is rotation angle is related to a, the ratio of the a. So here I try to explain you that this wheel rotates 3 times less. So, okay, imagine now, if you rotate this at certain speed, so this rotates 3 times smaller, isn't it? Have you ever tried on bike which has like you can shift gears? So if a front wheel is small and back is big, if you rotate, if you pedal, then the wheel moves very slowly if back cork wheel is very big. Isn't that right? Have you tried, have you ever used the bike which has gears and you can shift gears?
What
divided,
was the question?
My question is that have you ever had a bicycle when you just can't pedal? Have you ever had?
Yes.
Okay, so you know that the front is a rear cogwheel is big and the front cogwheel is small, then you pedal a lot, but the bike moves slowly, isn't it?
Yes.
Okay.
Yes.
Exactly what happens here. You pedal here, but this moves slowly. It must move 3 times slower. Now, Khalid, no, it is not. There is no reason to pi appear here. The angle in radians, by definition, is arc length divided by radius, not perimeter, but by radius. Khalid? Rotation angle, by definition, is arc length divided by radius. Khalid, are you okay? Yeah. Radians, angle in radians, yes. Usually in physics we work with angle in radians. All right, and now long story short, because this rotates 3 times slower than this. Once bike moves the distance 6, and this displays this here rolls, then here is slipping by 2/3 of x. Now, is that fact more or less clear to everyone that slipping distance is by how much two surfaces slip with respect to each other? Is 2/3 of x.
Mister?
Yes.
The first one on the right, it will stay at the same position.
You are speaking about this here?
Yes.
Yeah. So black represents initial position of the wheel, and red depicts final position of the wheel. And now this black line here, okay, maybe I should use a different color. So let me now let us at the initial position, let us draw one spike here which is vertical here and leads to contact point. So from the axle to the contact point, we draw at the initial position a spike. Now the wheel has rotated by x over divided by 3, and this spike is now in this position here. It rotated by x divided by r. And now if it rotated by x divided by r, new contact point is here, and the distance here on the horizontal surface is almost as much as
X.
Yeah. So this point here is above, just this point here is the end point of that spike just went up, and do not, because there was no slipping. It just raises slowly and does not slip. Okay.
Okay.
And now,
so the delta x is x.
And now here we do the same here. Here vertical spike, but now this rotates 3 times smaller, 3 times less than here. Here rotated so as much that this did not slip, but here this wheel rotates 3 times less, and now we see contact point is here, and the point which the end point of that spike, which was here at the beginning, is now here. And the wheel displaced by x. And if here the rotation was also x, so that the contact point is here, but the spike is turned so that it is still above the previously marked point, then now contact point is here, but it rotated only is 3 times less, and so this distance is 3 times less. And while contact point is here, the marked spike is here, so there was slipping by 2/3 of x.
So the total displacement for the system is 2x over 3.
Yes, it's how much is slipped. Yes.
Okay.
And now we are ready to go for the calculation of work done, the energy balance. And now on the one hand, it is F times x, the work what I do. On the other hand, it is equal to the work of friction force. So we can write now that work done F times x, work done F times x equals work lost to dissipation due to friction, which is now friction force at this wheel here, which is N1 times mu. But N1 is mg minus F divided by 2. So this is mg minus F divided by 2. This is N1 multiplied by mu, and then multiplied by 2/3 of x. Okay?
Okay.
And now here x cancels away, and we obtain expression for f. So from here, x goes away, and now f let me see what will be. We have now f multiplied by, here is 1. And if we bring this from right hand side to left hand side, then we have mu divided by 3. And at right hand side, we have mg divided by 3 times mu. Mu mg divided by 3, because 2 cancels away. So that f equals mu mg divided by mu plus 3. Okay, and this is the answer. Now,
It's clear.
yeah, okay, let us stop here. Let us not check if our assumption was correct or not, but I think it was correct. So I think it is correct answer. And let us see if it starts rotating earlier or later. Then normally it would be mu mg, but here is actually quite a lot less force is needed to apply. Like we have here factors 3 already. So
I have a question.
Yes.
What did you substitute x for?
Why did you substitute what?
What is x?
X is displacement of the whole thing.
Yeah.
So
In this equation, what did you substitute it for?
Here, x cancels away. X cancels away. It's the left hand side and right hand side.
Yeah, I just saw that.
Okay.
Thank you.
Yeah, you're welcome. This was the whole idea that both things are proportional to x, so x should cancel away.
Sir, what is phi exactly?
Sorry, what is?
What is phi?
Phi is rotation angle of the front wheel. Rotation angle in radians. So if it rolls by distance x, then it rotates by x divided by r. Are you okay with that?
Yes.
Mm-hmm.
I have another question. It's not related. The previous Zoom meetings.
Okay.
There are only the first 2 on YouTube, so where are the others?
They should be now there. I uploaded, should be everything over there. Did you check? At least I uploaded everything, and this morning they should be everything uploaded by this morning. Well, in the YouTube channel, I think they should be over there. I can check, but I think they should be there. Oh, I see. They are uploaded but not linked to the playlist. Okay, I'll fix that. Okay, now everything is up. Now it should be all fine. Yeah, it was just they were not the videos were not added to the playlist, and that's all. All right, shall we go on?
Mr. Everything is clear on this problem, but I have one question. The first equation, you suppose that the sum of the torque equals 0. Why is that?
Some of the talks are not because it is in equilibrium. If we push it slowly, it still does not move with acceleration, so it is in equilibrium. We should have force and torque balance. Okay.
Okay, clear.
Mm-hmm. Now, let us go to dynamics. Now, yeah, someone wanted?
First equation, F times R. How is the distance from the center to the point where you? How is it?
R is radius. R is radius of the wheel. So if we apply here force and consider a pivot point here, then the distance is R. So F times R is the torque with respect to this pivot point.
Yeah.
And then we have, all right. Yeah, actually here I wrote N1R and N2R. So I assume basically that this distance between the wheels is very small. So like this arm is also almost, yeah, in the figure you could say that actually distance is a little bit bigger, but we assume that this gap between the two wheels is very small. So the distance to here, from here to here is also R. So N1 times R then is torque of this force here, and N2R is torque of this normal force here. Okay, Lama? Is it fine?
Yes. Yeah.
Mm-hmm. Now, shall we go to the next problem? And now, yeah, before we go, tomorrow is test, all right? Tomorrow is test, and then level 4 students wanted to have test wanted to have test 10 o'clock starting. What about you? Do you want to have 10 o'clock, or you would want to have it earlier? Well, how do you feel? Tomorrow test. And with level 4, we did so that test was 4 hours, and we had reserved 2 hours for discussion, but we managed to discuss the solutions of the problems faster than that, so we finished a little earlier then. So tomorrow test, my suggestion is 10 to 15, 10 to, not 15, 10 to 14, 4 hours. Discussion of the problems 15 to 17, but possibly we can finish earlier. Is that okay with everyone?
Yes, I think it's fine.
Okay, then we'll keep it that way, because yeah, with level 4 we discussed it, and no one of them wanted 9 o'clock, so 10 sounded for everyone better, so we did it 10 o'clock. But someone even later. Well,
If it's possible, I'd agree with Wissam.
You would agree with what?
I agree with Wissam, if it's possible to make the exam at 12 o'clock.
We have 2 votes for 12. So if we have 12, then everything shifts by 2 hours. Now please type into chat if Khalid, what is your problem? PM, well, this is 10 a.m. until 2 p.m. And 3 p.m. to 5 p.m. is discussion here. Now, if you like to have a later start, then everything will shift by 2 hours. Now, please tell me if you want to have, say yes into chat if you like this. Khalid suggests 11. Well, you need, actually, I recommend you think also about your lunch. So how you would fit your lunch into here. So that might be also a good point. I think here, if we finish 2 o'clock, then 2 to 3 would be quite fine lunchtime, don't you think? On the other hand, if you make it 11 to 3 or 12 to 4, then you would need to have lunch before, or maybe you just wake up then. So guys, level 4 was fine with this schedule here. And as far as I can see that most of you are also okay with that. I know Wissam and Zara want 12, but now we have I have gotten let me see who responded. Let us not spend too much time on discussing that. So Khalid wants Elias. It seems to me that more votes are right now for 10 o'clock. Ali wants 12. Hussein, what about you? Okay, but let us indeed then make a compromise. 11 to 15, and then 16 to 18. Makes this everyone happy?
I mean, before 12, like 11 to 12, there's a prayer time. So it's like
So
It's-
so this
it's
makes
not-
it 12 to 16. But can we make then the break a little bit shorter here? Something like not. All right, all right. 16 and 17 to 19. Okay. That way then. Oh, now Lama is telling that 12 is not suitable. Oh well. There are 2 prayer times, but what if we extend it so you can take your prayer break between solving? So let us say you have to submit your solution at 17. We still have from 12 to 17, we have solving. So you have 1 hour for different breaks and prayers.
Oh, okay, that would be so good. Okay.
And then, but then we start all immediately more or less once you submit and we discuss. Because then I assume that you already have some breaks here and you are not too tired here then. Is it all right? Okay, it seems we have decided with that. Okay, let me write here. Test 12 to 17 and 17 to 19. Okay.
Oh, wait, so the test is 5 hours?
Sorry?
Test is 5 hours or what?
Yeah, it is 5 hours, but it is assumed it is 4 hours for solving, and you can have a break and prayer in between in total of 1 hour.
Okay, good.
But I assume the solving time here is 4 hours. Okay, and then let us go on. Now, what we are going to do now is a way to solve dynamics problem, which otherwise would be quite challenging, but with a method which is known as a generalized coordinate approach. You can solve it quite easily. And then, for instance, we consider a problem like that. Here we have a wall, and here we have a floor, and here we have wedge. And here goes a brick here. And here is a small wheel over which this can rope can slide. And here is angle alpha. And we're asking about what is the acceleration here. How would you solve this problem? Yeah, break up into vectors, but actually here is a small problem in that you need to, usually if wedge is at rest, then you can project forces in the perpendicular to the inclined surface so as to obtain force balance. But here the wedge is moving, and so there is no force balance like that. So it is not very easy to do that way.
Maybe we can change frames and assume that the wall is moving.
Yeah, we can go to frame where wedge is at rest, and then it is just we can write down conditions that it is stationary in perpendicular direction, but then we need to account also that there is force of inertia, which is minus m times a, and we need to keep this in mind that if I go to a frame which moves with acceleration, then there is a force of inertia. Are you familiar with force of inertia? Right, not really.
Mr. You mean moment of inertia? I?
Well, force of inertia is a force like it is called fictitious force. That if you you know that usually in school at least you are supposed to solve problems in inertial frames of reference which move with constant speed without acceleration. But actually, it is also possible to consider things in moving and rotating frames. But in that case, you need to add fictitious forces. And now, if frame moves with acceleration but without rotation, then in order to make everything make sense again and work out correctly, each body will have is applied force of inertia, which is opposite to the acceleration of the frame and given by modulus as m times a. So if we go to a frame which moves from right to left with acceleration a, then we have force of inertia applied here. And so the forces which are applied here is m times a from left to right, because it is minus ma. The acceleration of the frame is to left, but force of inertia is to right. And then we have here also m times m capital times a. Let us say this is m capital and this is m small. And then of course we have still gravity force, m times g, and here is m times g. So these are the forces what you have. And of course tensile force. Tensile force is here as well. Now, this is more or less if you go, if you sit into a car and the car accelerates, you are pressed back. Is that right? You have felt certainly that, yeah. Then this is, you can think this as a force of inertia because you are in a go-moving frame with car which accelerates, and then there is a force applied to each body minus ma. And this is what is noteworthy is that this is very similar to gravity force. Gravity is down, but this is opposite to acceleration. And as a matter of fact, this like fact is a cornerstone of the general theory of relativity, that force of inertia is essentially indistinguishable from gravity force. But let us not discuss this issue here because it is like more advanced, but just actually for physics in general is very important point, but not for you for the time being.
Mr.
Yes.
So this force of inertia is acting on the body that's accelerating or on the other system around this body that's accelerating?
It is so a force of inertia is a force which is applied to bodies if you consider motion in accelerating frame. And it is applied exactly in the same way to anything which has mass. Anything which has mass, gravity is down mg, and this is minus ma. Just identically behaves to a gravity force. And it appears if your frame moves with acceleration.
Okay, so here it's applying at the small mass m because it's accelerating to this triangle thing.
Yeah.
Right.
Yeah.
Okay.
Because for us it's much more convenient to consider things in a frame where the wedge is at rest. So we go to a frame of reference of the wedge. But wedge itself is accelerating. So our frame, because of that, is also accelerating. And then anything will have force of inertia applied.
Okay, makes sense.
Similar to force of inertia, there is also, if you go to a rotating frame, then there is a centrifugal force, which pushes you away from the rotation center. So this by modulus, it is equal to mass multiplied by centripetal acceleration. So be careful not to confuse here. You have centripetal acceleration. Centripetal is, let us put here also a vector sign, is omega square multiplied by radius vector. It is the same direction as radius vector, which means that from the center of rotation. Now, centrifugal force is minus omega square r and multiplied by m. So it is opposite. It is, sorry, it's the other way around. So this is towards the center and this is from, yeah. So centripetal acceleration, as the word says, centripetal towards center. So this is centrifugal from the center. And so if body moves along circle, velocity vector rotates so that the acceleration vector, okay, here is velocity vector. Now here is rotation center. Now at the next moment of time, velocity vector is here. And now the difference of those two vectors divided by time gives us acceleration vector. So here is v1, here is v2. Difference of those two, if we carry over this velocity here, it is perpendicular to the v. So it is along the radius vector here, and it is towards the center. Now, centrifugal force is if you go to some rotating platform or something, it will start pushing you away. It is centrifugal omega square Rm. So it is quite similar to force of inertia in that here we have mass multiplied by acceleration of the frame. Here we have mass multiplied by centripetal acceleration. Both are proportional again to mass. But with rotating frames of reference, it is not just centrifugal force which you have, but you have also Coriolis force. So if body moves in rotating frames, there is additional force, force Coriolis, which is something like a vector product omega cross v multiplied by m and factor of 2, something like that. Now, because this is like a little bit nasty expression with vector product, usually your problems will not, you should try to not use that your problems will not be on Coriolis force. Okay. So, but you need to keep in mind that rotating frames are dangerous. If you have just translationally accelerating frame, it is easy. You just add the force of inertia. If you have rotating frames, it is okay as long as you have statics problem, body is at rest. In that case, you have centrifugal force. But as soon as body start moving, then you have also Coriolis force, and this makes a little bit nasty. All right, but actually our plan here was not using, not solve using this thing here. Also with this, you can solve the problem also nicely, not too difficult, but actually there is even easier way of doing it. So now we are going to, our approach is going to be based on the method of generalized coordinates. And now question, what is it? And the main idea is, like before, let's say it is somewhat similar to the virtual displacement method. We also, we consider virtual displacements, but also velocities which appear. So basically, you write down energy conservation law and take derivative of it. So the first step here, if we apply this method of generalized coordinates, is to write down energy, full energy. Actually, first step is introduce one coordinate which describes the state of the system. Introduce coordinate. Second step is express energy. Now introduce coordinates. So how can we describe the state of the system? Now I am going to clean these things here. Now let me redraw this. So introduce a coordinate which describes the state of the system. For instance, the displacement of this wedge here. Let's the displacement of the wedge be x. And then in terms of x, what is the energy? Well, energy, kinetic energy, of course, does not depend on x, but on the time derivative of x. So we are going to express now kinetic energy in terms of time derivative of x, which we denote as x dot, and potential energy in terms of x. Now, first, potential energy. Potential energy, it is just the energy of this thing here in gravity field. So if this wedge goes to left by x, then the rope moves down relative to the wedge also by x. So this guy here is going down the slope by x. And so vertically down by x times cosine alpha. So now potential energy is, energy becomes less because it goes down. So it is minus mg and sinus alpha, because it goes down by, and multiplied by x. It goes down by x times sinus alpha. And so potential energy change is minus mg sinus alpha times x. Is that clear? The potential energy expression?
Why is it sine alpha?
And alpha is here because if wedge moves from right to left by x, this distance here becomes shorter by x. This hanging part of horizontal part of rope becomes shorter by x. So inclined part of rope becomes longer by x. So this brick here slides down along the slope by x, but vertically x times sinus alpha. Is it okay?
Yeah, clear.
Mm-hmm. Now, kinetic energy. First, wedge. Wedge moves horizontally with speed equal to time derivative of x. So the kinetic energy is mx dot squared divided by 2. This is the kinetic energy of the wedge. Now, the kinetic energy of the brick over there is a little bit more complicated, because now we need to calculate a vertical kinetic energy and horizontal kinetic energy. Now, vertical kinetic energy. Vertical kinetic energy is because vertically it moves x sinus alpha. So time derivative of x sinus alpha is x dot sinus alpha. So vertical velocity of this brick here is x dot square sine square alpha and m over 2. So plus m over 2 sine square alpha x dot square. This is vertical kinetic energy of the brick. But then there is still horizontal speed. Now we need to calculate the horizontal speed of this brick in lab frame. In the wedge frame, it has speed x dot cosine alpha. But in a lab frame, we need to subtract the speed of the frame, which is x dot. So it is going to be now plus m over 2 and 1 minus cosine alpha square x dot square. And this is now full kinetic energy.
Wait, mister, what's the last term you added?
Yeah, sorry. No.
And what does it represent?
This is horizontal kinetic energy of the brick because the speed of brick, horizontal component of velocity in the wedge frame is x dot cosine alpha. But we need kinetic energy in lab frame. So we subtract from there the speed of a frame, which is x dot. So x dot cosine alpha minus x dot is the speed in lab frame. And in order to get kinetic energy, we take this to square. Is this fine?
So it's the velocity of the mass m in the lab frame times the mass over 2.
Mass of this thing here in lab frame, horizontal component squared times m over 2.
Okay. And why is it 1 minus cosine alpha again? Because I understand, but like
Because in wedge frame, the speed, horizontal speed is x dot cosine alpha. Okay, in wedge frame. V horizontal is x dot cosine alpha. Lab frame is Vx prime is x dot cosine alpha minus x dot. Okay, and we take this to square and we get this.
so it's similar if we take the total displacement in the horizontal axis and then we take the derivative, right?
Yeah, so a displacement, take derivative, get dots, and take to square to get kinetic energy. So x dot represents time derivative of x. This is a displacement.
Okay.
Well, then why is it not cosine minus 1?
Yeah, just could have written also cosine alpha minus 1, but minus 1 squared is still plus 1, so the result is the same. Clear to everyone?
Mr. I have a question. For the big body with mass m capital, why didn't we subtract for the frame?
I worried that it should be the other way around. I can write you cosine alpha minus 1 if this is what you mean. But it is still the same. Vx dot.
No, I mean our frame is moving to the is moving with the velocity or with acceleration.
Our body moves with speed x.
No, our frame.
Our
The
frame
other
moves
frame.
with speed x dot. X is displacement of the wedge, speed of the wedge is x dot. Our frame moves from right to left with speed x dot. Our brick here, so this moves from right to left with x dot. A brick over there moves from left to right at speed x dot times cosine alpha horizontally. Now we need to add them up, but they have, because one moves left and the other moves right, so we have minus sign over there. Speed in lab frame is the speed of the frame plus speed in the frame. And one is left, the other is right, to right, then they have different signs. Physically, I wrote here, Vx is x dot cosine alpha minus x dot.
Okay, can we continue now?
I hope so. So is it clear now to everyone? Khalid, are you okay? All right, now the final step. Final step is write down energy conservation law and take derivative. Derivative of energy conservation law. So we have the whole thing now is mx dot square divided by 2 plus m over 2, and here goes sine square plus cos. I open the braces. Sine square plus cosine square gives me 1, and then there is still one more 1, so this gives me 2, and then the cross term minus 2 cosine alpha, so minus 2 cosine alpha, and then x dot square. Now this is kinetic energy, but there is still potential energy, and this is minus mg sinus alpha times x, and this is constant. Now this is energy conservation law.
Sir, can you write with black instead, because red isn't very clear in the camera.
Yeah, okay, all right. Black was already like not writing too well. Let me write it something. Let us see if green right now well. So m x dot square divided by 2 plus m over 2, 2 plus 2 minus 2 cosine alpha times x dot square minus mgx and sinus alpha, and this equals constant. Okay. And now we take time derivative of, from here. And here we need to apply chain rule, because we have need to take derivative of x dot, and then first derivative of the square function is.
Mr. I have a question. Why does minus? Like, why kinetic energy minus potential energy?
Because potential energy high if body is high up, and low if it's falling. So here body descends, so it goes down, so energy is negative. Body has potential energy if it's high, and it doesn't have it is low. So if it goes down,
Okay,
it
I see. Because I thought you added a minus sign to the energy, but then I realized it's actually minus.
From the beginning, it has from the beginning.
Okay.
Now we take the time.
So we add the two energy and it's equal to constant. That's it?
This is energy conservation law. Kinetic plus potential is constant. You know it.
Yes, we know.
And now we take time derivative from here. So the time derivative of this term here, quadratic function derivative is 2 times. This gives 2 times x dot. So 2 goes away. Time, if we take here time derivative x dot, but then we have still, according to chain rule, we need to multiply this by the derivative of x dot. And derivative of x dot is x double dot, which means the second derivative of x, the second time derivative of x, which is acceleration. Actually, x double dot is the acceleration. And here happens the same thing, plus m 2 minus 2 cosine alpha and x dot x double dot. And then here we have minus mg x dot sinus alpha, and constant derivative gives 0. And then we see that all terms have x dot, so this cancels away. Okay. And now we are ready to express here x double dot, which is acceleration. X double dot equals acceleration is now m g sinus alpha divided by m plus m2 m1 minus cosine alpha. And this is the answer. So we obtained the acceleration, what the wedge will take.
Isn't it 2 minus 2 cosine alpha?
Yeah, I brought a factor 2 before the braces.
Oh, I didn't see that.
Okay.
Mr. I have a question. For
Yes.
the kinetic energy of the body with mass m capital,
Mhm.
it should be 0 because in the frame we should subtract x prime. Why didn't we subtract?
About what you are speaking, which line here?
The second line, the kinetic energy for the body of mass m capital.
Here.
Yes,
And which term here?
the first one, mx prime squared over 2.
Mx dot squared over 2. It is not prime
Yes.
x dot. A time derivative denotes by wedge dot. Now, this is a kinetic energy of the wedge in lab frame. So we assume the wedge moves in lab frame by x. So time derivative of it is x dot. This is the speed of a wedge in lab frame. Kinetic energy mv squared divided by 2. So that's it. How you feel about that?
So why did we subtract x dot for the mass m small and we didn't
Why did you do it here? We
Yes.
did it before here because we needed here the speed in lab frames. This is speed in lab frame. But when we studied this brick here, we first went to wedge frame because we were able to easily figure out how it moves in wedge frame. In wedge frame, it just moves out, down by x, but down the slope by x. So this whole thing here stands for the kinetic energy in lab frame. I wrote it here, also explained it in step by step. So in wedge frame, it moves down the slope by x. So the speed in wedge frame is x dot. But it has component horizontal and vertical. Now, horizontal component x dot times cosine alpha is the horizontal component of the velocity of this brick here in the wedge frame. But we need a horizontal component in the lab frame. And in lab frame, we need to add the speed of our frame, which is x dot. So we have x dot cosine alpha is the speed of the brick in wedge frame, and then in opposite direction we have x dot the speed of the wedge. And we add the bar up and obtain this horizontal component of velocity in the lab frame. And here goes the velocity kinetic energy in lab frame, which is the speed squared in lab frame.
Okay, clear now. Thank you.
You're welcome. Okay, shall we move on? Then next problem. And next problem, you try to solve it yourself first. And it goes like that. We have here inclined surface and angle alpha. And here we have another inclined surface. And we have also angle alpha. And then we have here a wedge. So here is also angle alpha. And then we have here a wall. And then this has got a mass m capital, and this has got a mass m small. And now you need to find acceleration of this ball. Okay? No friction, nowhere. Is it clear? Is the problem clear?
Ah, yes, clear.
Okay, then please try doing it.
Mister, what do we need to find again?
What is your question?
I forgot. What do we need to find?
You need to find acceleration of this thing here. Now there was question if you can have a prayer break before solving. It's up to you. If you want to do the prayer break right now, you can do that, and then you continue. Just just as you like. Because probably either way, you are not able to solve it before prayer break, you need a little bit more time. So whether you have now prayer break and then solve, or you first solve and then have break and then solve after that, continue solving, it's up to you.
Sir, are the slopes fixed?
Sorry?
Are the slopes fixed? Do they move?
These things are fixed, of course.
Okay.
Wait, mister, are they fixed? I mean, if they're fixed, how would any movement happen?
Well, these are fixed, but these slides, no, there is no friction
Um,
along the slope. No friction, of course, they start sliding.
I mean, I assume that these slopes are going to move one of them
This
to the
is
right and the
fixed
other to
space.
the left.
This is fixed. This is fixed. The wedge and the ball move slide on these slopes.
Upside,
Sorry?
up. They're gonna move up, like.
Who knows? One moves up, the other down, apparently.
So there's this gap, and it counts.
Sorry?
I mean, there is a gap between the two slopes.
Yes, there is a gap. Yes, small gap.
Okay.
So how are you? I have already few answers. Yes, very good. Lama and Khalid got something, and I think, yes, these are correct answers. Now, please, next task, find the normal force between this and that. Once you have the Lama and Khalid, you can proceed next task, find normal force between this and this. Okay?
Between what and what?
Normal force.
Okay.
Okay? Lama, your answer for normal force is not correct.
Mr.
Yes.
So I have a problem. When I move this the triangle by x up, I can't find the displacement of this circle.
Oh, what? Well, this is like the main step. If this displaces by x down, now this distance along the slope is x. Now this ball moves horizontally. Okay, horizontal displacement is x times cosine alpha. This ball here displays horizontal x times cosine alpha. And so ball displays horizontally also x times cosine alpha. But because this is only horizontal component of displacement, vertically it goes by x times cosine alpha divided by cosine alpha, so it goes up also by x.
Okay.
I still don't see any correct answers for normal force. Lama, your new answer is a little bit better, but still not correct. Now, Khalid, your acceleration. Let me see it. No, there should be no term like sinus alpha, cosine alpha. This is something that went wrong. Now, some it's like what does that 2 sinus alpha do there at the end? This is something strange you have over there. So now, guys, shall we solve it together?
I don't know. I feel bad because I'm not getting anywhere with my solution. So I think yes, we can solve it together if the others are okay.
Ali wants 3 minutes. Okay, I will give Ali 3 minutes. Khalid, just you shouldn't have terms like sine alpha, cosine alpha. I don't know where Khalid you went wrong, but that's you shouldn't have. But Khalid, your acceleration, Khalid, is the first acceleration which you gave me. This is correct. If 5 or 5, we should type in this acceleration, Khalid is correct. Lama, that should be something like a term, something like n minus m divided m minus m divided by m plus m, or something like that should appear. So your answer is like there should be something more than just sign mistake. Yes, Khalid, that might be the case. No, Ali, your answer is not correct. So shall we try to solve it now together? Everyone ready to do it together?
I'm ready.
Okay, so here is kinetic energy and here is potential. So one goes up, the other goes down. So one has plus, the other has minus. Whichever we have as plus, which we take as positive, this depends how our convention. If we assume that m small is bigger, then m goes down and has minus, and m capital is smaller and goes up and is positive. Now,
So is it still correct?
Sorry?
Is it still correct if we assume that M capital is bigger?
We can make it the other way around. If we want M capital to be bigger, like then it would be M minus M capital then. Just
So
if we
both-
obtain negative acceleration, so this means that the sign was the assumption is like the opposite. And now we take time derivative of the sum, and we obtain mx dot x double dot plus m capital X dot x double dot plus gx dot sinus alpha m minus m, and from a equals 0, and here we obtain x double dot equals m minus m divided by m plus m and g and sinus alpha. Okay.
Wait, mister, how did we get to the velocity?
Velocity, this is acceleration. Velocity cancels away because it's in all the terms.
Okay.
And now normal force. Normal force we get from the Newton's second law. We project motion so that one normal force goes away. So a normal force, let us say this ball here, we project motion into this x-axis, let us say. And then we have m times x double dot is the acceleration of this guy here. Well, we assume that it goes down, so let's put the axis down then, axis that way. Now we assume that it goes down, and I plug in here expression for x double dot, so it is m minus m divided by m plus m g sinus alpha. This is mass times acceleration, and this must be equal to now projection of the gravity force to this direction. So this is m capital G and sinus alpha. And this gravity is down, moving it down. And then we have normal force, which is in that direction, so it goes with cosine. So, but this is opposite, so it goes with minus n times cosine alpha. Okay?
Why multiply, not divide?
Why what?
Why multiply cosine alpha, not divide cosine alpha?
I still, please repeat once again.
Why is it multiply cosine alpha, not divide cosine alpha?
Because normal force is horizontal, but we took projection to this axis here. So horizontal, we project into this direction, it gets multiplied by cosine.
Can you draw the triangle?
Yeah. And so you get n equals now g sinus alpha, and then we have m capital, and then we have m capital minus m small divided by m plus m small, and minus 1. Minus 1, and if we bring to the common denominator, m capital goes away, and this becomes, can you see it? Yeah, you can, more or less. This becomes 2gmm sinus alpha and divided by m plus m. Okay. Everyone happy with that?
Oh, yes. Can you make the whiteboard as a full screen so I can take a picture?
Yeah, sure.
Okay, thank you.
Mr. I have a question.
Yes.
I'm confused. Why it is minus n cosine alpha?
We need to be careful with these signs. So we project into this direction, downwards direction, because we assume m capital goes down. So we have mass times acceleration down. This is this thing here. And this equals forces towards the downwards go with plus. Because acceleration is downwards, also forces downwards go with plus. And gravity force has the downwards component. So it goes mg sinus alpha. But normal force is opposite, it's pushing it up, so it goes with minus.
No, I mean why it is times cosine alpha. I think it should be divided by cosine alpha.
The force which is exerted by normal force to this m here, it's directed like that. Here is alpha. We project it to this direction. So if we project to this direction, it goes with cosine. Are you okay?
Yes, okay now. Thank you.
Now, yeah, so here first is to use Taylor's coordinates to find acceleration. Second, Newton's second law, using the acceleration, what you found with the help of Newton's second law, you found force. No.
Should it
Yeah.
be sine alpha or tan alpha?
Oh, yes, this goes tan alpha. Yeah. Final answer is, of course, tangent. Okay, let us fix it. For normal force, yeah, we have tangent. Now, let us make one more exercise for you. And are you ready? Then I clean. And now we have inclined surface. And here is a carrot vehicle like that. So the total mass of wheels is m small. Total mass of wheel. Okay. And then we have this body, which has a total mass of m capital. And here we have angle alpha. And we have, starts going rolling down. No, it goes rolling down. Wheels start rotate both. And we ask, what is the acceleration here now? And these are solid disks. So a moment of inertia for solid disks, who tells me?
mr square.
If it's solid disk, it is divided by 2.
Oh, yes.
Yeah,
It's not a
will
ring.
be like a mass on the rim, then it is a mass square. But so what is moment of inertia is this such as sum equals sum of all the small masses multiplied by the distance from the rotation axis squared. Because here all the masses are equal distance, so it goes mr square. But here some are closer, some are faster. So root mean square average of distance squared is 1/2, gives you 1/2 here. Okay.
Can you just explain what's happening?
The carrot, which has 2 wheels, front wheel and back wheel. The total mass of wheels is m small, and the body has mass m capital, so not really like fixed part. And then this starts accelerating down due to gravity. Gravity is downwards. And wheels roll on the surface, no slipping. And the question is, what is the acceleration? What is the acceleration here?
Mr. What's m capital?
Sorry, m capital is the mass of the body. So here
Of the whole
is
system or this body?
This is the body of the garage. So here they are fixed on axles, so you can wheels can rotate freely.
Okay.
It's like bike. These are wheels, and this is the body of a bike.
What is the
Yes, someone wanted to ask something?
moment of inertia is for what?
Moment of inertia of a wheel of mass m is mass of the wheel radius squared divided by 2. So you know what to do with moment of inertia. Have you worked rotational problems?
Yes, kinetic energy, yes.
Yeah, kinetic energy is I omega squared divided by 2.
Mr. If we added the kinetic energy with omega 1, we don't have to add the one with the velocity v, right?
When you calculate kinetic energy of a wheel, there are 2 ways of doing it. First is that you can calculate the moment of inertia respective to the instantaneous center of rotation, because all the velocities are as if the body were to rotate around the instantaneous center of rotation. But in that case, you need to apply parallel axis theorem to calculate the moment of inertia respective to that axis. The other way is to calculate the moment of inertia as the moment of inertia, the kinetic energy as the kinetic energy in the center, in the frame of reference of the center of mass, and add the kinetic energy of the center of mass. So we say that kinetic energy is kinetic energy of the center of mass, m total v center of mass squared divided by 2, and plus ek prime, which is the energy in the frame of center of mass. Okay. So if you go up to the frame where the axis of the wheel is at rest, you calculate the kinetic energy of the wheel, but then you need to add the kinetic energy of the center of mass, which is a mass of wheel squared, speed squared divided by 2. This is like more, probably this is more easier to apply, I think, this way.
Wait, Mr. So the kinetic energy is equal to the kinetic energy of the center of mass plus
Kinetic energy
what is
in the
this
center of mass frame. You consider motion in this frame of the center of mass. And if you take, for instance, a wheel which rolls down, then if you go to the center of mass frame, then the wheel just rotates in that frame along this axis, right? Then this moment of inertia is given for the axis which goes through the center of mass. So you can apply then this. Is it okay?
Yes.
Sir, what is the
Thank
radius?
you.
What is what?
What is the symbol for the radius here?
What is the what did you ask? What is the radius? Radius, if you need it, just let us say R capital.
Okay.
Is it given?
I don't think you need it.
Mister, can you check my solution?
What did you want?
Can you check my answer?
I'll check your answer. No. So just to make sure, M is the total mass of the wheels. If the front wheels plus back wheels, the total mass. Okay. But the answer is no, not correct. There is more than one mistake in your answer.
Okay.
It is not just one mistake. Just look carefully over and try to be careful.
Okay, but I just want to make sure what's M again.
M small is the total mass. So if we have two wheels, then mass of each of the wheel is m over 2.
Okay.
Mhm.
Sir, can you explain the kinetic energy part?
Can I explain what?
The kinetic energy part.
How to calculate, you mean? Well, so total kinetic energy is the kinetic energy of the center of mass, which is a total mass multiplied by speed squared divided by 2, plus the kinetic energy in the frame of the center of mass. So if center of mass moves together with the carrot, then in that frame wheels rotate around axis, and so you need to add a rotation energy in that frame, which is I omega squared divided by 2. Each of the wheels has a kinetic energy I omega squared divided by 2, where I is the kinetic energy, the moment of inertia.
Okay.
Mhm. So Lama nominator seems okay, but denominator, I think that should be slightly different. I think you have probably the kinetic energy in the frame of reference of the center of mass should be, you check how you calculate it, what you got for the kinetic energy in the frame of the center of mass. And Sarah, the same applies to you. Now both of you have quite both of you have quite nice answers already, but still not entirely correct. So check the kinetic energy in the frame of the center of mass. All right. Don't forget that it is 1/2 I omega square, and I is 1/2 MR square divided 1/2 MR square. Don't
Mr.
forget
R's
that.
from where?
Sorry.
Wait,
Moment of
so
inertia
the
of a
kinetic
wheel.
energy.
Yeah, moment of inertia of a wheel is 1/2 MR square. Okay, check that if you calculate this properly.
Yes, I did that. I mean, I don't know where's the problem.
The problem is in
Maybe-
your problem is in your denominator. Denominator means kinetic energy went wrong.
Mhm.
And nominator is okay, which nominator comes from potential energy, and that is okay. But denominator, well, the mass of the carrot is also okay, but then the mass of the wheel is not okay, which means that probably you made mistake when you calculated kinetic energy of the wheels. And you did not take account properly that 1/2, which is in the moment of inertia. That is my guess. All right, check it.
Okay. Mr. The first term of the kinetic energy is the mass of the whole thing times the velocity over 2, right?
Yeah, yes, and this thing, this thing is you have m capital plus m small is a mass, mass of the whole thing. Yes, that's entirely correct. But then you add m mass of the wheels times velocity squared for the kinetic energy in the frame of reference of the center of mass. But that is not correct. What is wrong in your case is kinetic energy in the frame of the center of mass, in the frame of the wheel, of the carrot. Okay, check the kinetic energy of rotation in the frame of reference of the carrot. Now, as some that is not correct. And there is no speed given. Acceleration v is not given. Acceleration should be in terms of masses and g and alpha.
answer. Hello, Mr. Can you see the solution?
Khalid, yeah, you have exactly the same expression. No, it's you have missing. Yeah, now denominator is okay, but nominator is now wrong. You now check your potential energy. Potential energy comes both from wheels and from the body. So yeah. Mohammed, you have more or less okay, except nominator should be 2 times bigger. So probably check your kinetic energy. You probably forgot one factor of 2 when taking derivative. Perhaps if you take square derivative of squared function, 2 comes up. Check that. Mohammed, did you get it? When you take derivative of x dot squared derivative, then this is 2x dot x double dot. Check that if you have that 2 over there, that you didn't forget it.
Okay.
Zara, there is no speed given. You shouldn't have speed. Okay, kinetic energy, yeah, right. Kinetic energy, let me see. The first term is not correct. No, sorry, the second term is not correct. Because moment of inertia with respect to the center of mass is 1/2 mr square. And m and so kinetic energy of the wheels in the center of mass frame, okay, is now number of wheels. Let us say that we have 2 wheels, and total mass divided first 1/2. 1/2 comes because you have everywhere in kinetic energy is 1/2. And then we have a number of wheels, which is 2. Because we have 2 wheels, we have factor 2. Now, but each of the wheels has mass m over 2. So these 2 cancels away. And then goes moment of inertia, which is mr squared divided by 2. Then mass is already here, r squared divided by 2. And then goes omega, which is x dot divided by r and squared. So this r goes away. And what you're missing probably is this factor 2 here.
Okay, yes, I see
Okay.
now. Because I thought that this 1/2 is for the energy, not for the energy moment of inertia.
I many times said that pay attention to this 2
Yes, you said that.
I said you many times that check this. There is another 2 here, but this one here.
Yes.
Okay, now you know how to do it. All right.
Okay, thank you.
You're welcome.
Can you see mine?
And now Khalid got now a correct answer. Yes, very fine. Now Mohammed has also now fixed the expression. Now anyone else has a fixed expression. Lama, did you have correct answer?
I just sent you, did you see?
Okay, yeah, Lama, this is correct, yes. Now, Zara, what about you?
I'm correcting my answer now.
Okay. Just a few minutes for you, yes. Anyone else hopes to finish? Hussein, how are you? Do you have answer? X is displacement, now velocity. Okay, and then let me take notes. So what this time we got Lama Khalid and Lama and Mohammed. And then Sarah probably will get also it. And then we can go to the next problem. Meanwhile, I can give you a next problem already, so you can start thinking. Okay, so next problem. I'll put next problem here at the corner here. Now, now we have YouTube, which is filled with water. And this length of that part which is filled with water, this is L capital. And your task is to find now the frequency of small oscillations. Oh yeah, so prayer break, we have, someone is asking, no, we have a prayer break, but prayer break, I think you have had it. This was prayer break. Now, right now it's 19:12. Okay, according to my clock, you have still 20 minutes until break. Am I right? Because I had it here from 7:30 to 7:40, but right now we are still missing 20 minutes. Is that okay? All right, then 20 minutes, after 20 minutes will be a break. And now you have YouTube, which is filled with water, and I ask about frequency, circle frequency of small oscillations. Now, do you know how to calculate frequency of small oscillations? Just in case, very fast. So for instance, if you have here spring and mass. So if we displace the spring by x, then the equation of motion is mass multiplied by second derivative of the displacement. This is acceleration times mass. According to Newton's second law, is minus k times x.
Mm-hmm.
And then the ratio of these factors here,
Omega squared.
states that if we have equation in the form of x dot equals to minus omega square x, then the omega is the circular frequency of small oscillations. So basically, this factor, if you divide by m, then vector which will be coefficient of proportionality between x double dot and x is the circular frequency. So basically, you need to do the same thing here and find circular frequency of small oscillations. Is the task clear?
Yes.
Okay. Now, Zara, did you get answer? Let me see. Yes, Zara got also correct answer now. Yes, and then let me do it fast. Those of you who have got already correct answer, you can actually start doing the next problem. But meanwhile, I'll show you how this problem was done. So we calculate here the kinetic energy of this thing here as the sum of energy in this of the center of mass, which is m plus m multiplied by x dot squared divided by 2. And we need to add kinetic energy in the frame of the center of mass. And that I did already. So this is now 1/2, which is from kinetic energy. Then we have 2 wheels, but each wheel has half mass. And then we have a moment of inertia, I and omega square. But mass, let us see, it gives that m over half goes to I. 1/2 and then I omega square. Now I is half of the mass because each of field has m over 2 as mass. Then 1/2 because it is cylinder, it is a factor there is 1/2. And then it is r squared. And now r times omega happens to be x dot. So if we simplify it further, then we obtain m plus, and now this gives here m, those two goes away, but here will be m over 4. Here is 1/2 before, so 1, 2 is in the denominator more. So we need to have half m here, so it will be 3 over 2m. And x dot squared divided by 2. And this is kinetic energy now. And then potential energy equals now minus m plus m multiplied by g, x, and sinus alpha. And now derivative of this plus that is going to be now m plus 3 over 2m x dot x double dot minus again equals, I bring this to the right hand side, equals m plus m g x dot sinus alpha. So x dots goes away and we obtain x double dot equals m plus m divided by m plus 3 over 2m g sinus alpha. By the way, this was like once it was such kind of problem was something like 10 years ago, an IPHO, part of IPHO problem, not whole problem, but part of it. So, so yeah. But now you have next problem. And next problem is to find frequency of small oscillations of water in your tube. Okay. Moment of inertia, no, moment of inertia is mr squared divided by 2. This here, because this is mass is m over 2. Yeah, in that sense, yes, it's m over 4 because mass of each of them is m over 2. So in the formula of the cylinder is 1/2 mass radius squared, but mass is 1/2 Best sum. Is that clear? Because we have 2 wheels, I multiply this by 2, but each of wheel has mass m over 2. Mohammed, are you what now? What are you doing? You are express me the frequency. I ask for circular frequency, not frequency. Are you giving me the circular frequency or frequency? frequency, but I asked circular frequency. So remove your pi and give me omega. Yeah, I think that is correct. I think that is correct, Mohammed. Yeah, very good. Mohammed, do you want to have another problem? Okay, so next problem after this YouTube problem is that we have one vessel, cylindrical vessel was cross-section area A capital, field which has water in it. And then we take another cylinder, which is empty inside. And then the mass is negligible. Mass of this cylinder is negligible, it's filled with here. And we ask, what is the acceleration here? Okay, now, yeah, what is the acceleration? This goes up. And now, let us say that cross-sectional area here is B. Here, this is cross-sectional area is A, and here it is B. Mohammed, is it clear? Zara, answer is not exactly correct. Because you are missing factor 2 or something like that. Yes?
A small, what is it?
So we have a cylinder of cross-sectional area A capital filled with water. We put another cylinder in it. And then we ask what is the acceleration of this thing here up? And let us say that the depth where it sits here is, you probably it will cancel out, but you can say it is L. And L is much larger than this cross-sectional, this diameter here. So L is much bigger than the diameter. The L is a height which is filled with water. Is this clear?
Yes, okay.
Mm-hmm.
Mister, is my solution correct?
No. Unfortunately, no. Factor is not correct. Khalid, yes, you have got it right. And Zara, frequency cannot be square root of L divided by G because dimensionality goes otherwise. If L divide L by G, it would be seconds squared, and take square root, it is seconds. So frequency cannot be in seconds. Okay, so a new problem is that you have a cylinder here, which is filled with water, and you have another cylinder, which is empty, with zero mass, inserted into here. And now the question is, with which acceleration will start this going up? And here you are given a cross-section area here and cross-sectional area here. This is A and this is B. And the length here of the region which is filled with water is much bigger than the diameter of these vessels.
What can you repeat last point?
Sorry?
Repeat last point. What is L? L much bigger.
L is a length which is like from the bottom of the inner cylinder to the water level. From the bottom here to the water level is L capital. And this is much bigger than the diameter.
Which diameter?
Whichever, they are very close. We assume that A is similar to B, so which diameter? Both diameters have the same order of magnitude. Inner and outer cylinders have the same order of magnitude for the diameter.
Mister, I sent you my solution in the chat. Can you check if it's correct?
Lama? Yeah. Jumana, yes, the answer is now correct. Yes, this answer is correct. Yeah.
What about mine?
So a solution of the answer of Lama is not correct. So there should be no pi. Where do you get pi, Lama? There shouldn't be any pi in your expression. How did you get pi? Because here you have second derivative proportional to displacement, and proportionality factor gives you frequency squared. No pi emerges anywhere. So please check how did you get pi. We are asking circular frequency, not normal frequency, but circular frequency. Zara, no, it is not square root of G of L. Now dimensionality is correct, but there is a numerical factor wrong. Now please tell me when you are ready to do it together. But I guess now is your prayer break, so 7:30 to 7:40. So
Mister, just give us 5 minutes.
yeah, okay. 5 minutes after break, and then I'll do it. How are you? Yes, density and L are, well, if you need L, I don't think you need L, but I think they are known, yes. Okay, so shall we solve this? No? Can we solve this problem now? Hussein, can we solve this problem now? Romana, shall we solve this problem now? Just because the previous chat was disappeared. If you had answer for this, please type once again answer for this problem here. For some reason, suddenly previous chat disappeared.
Mister, I'm trying to send my answer, but they're saying that you are not in this meeting for some reason.
I am. Just type in. Just type in. I am here.
Yeah, I know you're here because I can see you, but whenever I type
Yeah,
something, I can't send it.
Something strange happened. Try once again.
Okay, I'll try. They're still saying that you're not in this meeting. But like, my answer is the square root of 2g over L. I'm not sure if it's correct or not.
Okay, all right. So Zara, you had square root of 2g of L, was it?
Yes.
Okay. Now, anyone else wanting to type in their answer? Khalid Muhammad, also please type in. As mentioned, chat, there was like a certain interruption in the Zoom meeting, so it's continuous recording. I don't think there was. Luckily, it is still a single recording, but something for chat disappeared. Okay, all right. All right, let us do it now together. So what happens here is that if it takes that this goes up by x, then this goes, of course, down by x. And then this mass here goes from here to here. Now, if this is x, then the height difference of center of mass is also x. So we have it as if mass of water replaced to here. It is raised by x, and so potential energy now P equals total mass divided by the length. This gives a mass of a unit length. Multiplied by x, this gives us a mass which was displaced, and multiplied by gx, and this gives us potential energy. Now, kinetic energy is, of course, m divided by 2 and x dot squared, because all the water moves with the same speed x dot. And now, as usual, we have, actually, you can see m cancels out, and we have gx2, gx dot comes from potential energy, and then from kinetic energy comes 2 cancels away, because here we have 2 in the denominator as well. So it is x dot x double dot equals to 0. Yeah, I forgot L here. I forgot L over here, and then we have x double dot equals minus 2g divided by L and x.
Not C.
Okay, yeah. So x double dot, if we express from here, is minus 2g over Lx, so that omega square is 2g over L. So omega is square root of 2g over L, as many of you correctly typed. Okay.
Okay, Mister, the potential energy is what?
Potential energy is mx square g over L, and it is calculated as we have, if this is displaced by x, it's effectively displacing water from here put into here. Like here level became lower by x, here by higher, it became higher by x. And we have as if effectively replaced water taken from here and put into here, which means raising by x. So mass gx, but mass is overall mass divided by length and multiplied by this x gives the mass of the water which was displaced. mx over L times gx. So x goes to square then.
I don't feel like I understand the change in potential energy. I mean, I solve it in another way, but like I want to understand this way. It seems easier.
So initial is potential energy we can calculate related to the initial state. Initial state level here was equal to level here.
Yes.
But now here is what the level is raised by x. And so now we do have water here, the black we do have here now. Here we do have, but we don't have any more water here. Okay, so the water was taken here and put into here. You can think of it in that way. Because in this part, water was before and is after, so potential energy, no change in potential energy. But it was here and no longer is, and now it is here. So water was moved from here to here, which means that because this is a level, so center of mass was here below by x over half was center of mass was here now at the height x/2 below the water level, and now it is x/half above the water level. So now
Oh, okay. Because I thought it would be x/2, but now I see it's x.
Yeah.
Okay.
All right.
Thank you.
Yeah, you're welcome.
Mr., when do we use the energy? Like, do we always use the energy and then take the derivative? Or is there some certain cases that it seems like it will be easier to use the energy?
Yes, as long as you can describe state using one single coordinate, then yes, this is the easiest way to obtain acceleration by taking oscillation frequency like this here. As long as you can express the energy in terms of single coordinates, then yes, this is the easiest way. There might be cases when you need to more than one parameter to describe, but this we will be doing when you get to level 4. Let us not do it right now. Let us keep right now things simple, that if you have 1 degree of freedom, which means that you can describe the state using a single coordinate like here or here, or in all the cases before, then you just write down total energy, take derivative, and there you are, you get the answer.
I see.
Mm-hmm. And now you have this problem here. Here we have a cylinder of cross-sectional area A capital, small cylinder of cross-sectional area B. A is very close to B, and then the depth where out of which is put into water, immersed into water, is L. So L is the height difference between water level and the bottom of this inner vessel. And you asked about the acceleration of this vessel here. Mass of the vessel is very small, you can put it 0.
So L is the same for both sides, and it's the length of the water between the two cylinders, correct?
L is the height difference between the water level and the bottom of the vessel.
Okay.
And L is much bigger than the diameter. So you can say that this water fills a long region here. And
I see.
And then also you are given cross-sectional area of the big vessel and the small vessel. They are very close to this very only a small layer of water here.
What's M? The mass of what?
Mass of the inner cylinder is very small. You can neglect it. So inertia is given by the mass of the water. Mass of water gives you the inertia.
And we need to find the same thing.
Yeah,
the frequency.
The same thing. Yeah.
Okay, I see.
Acceleration of this vessel here, the inner vessel here.
Oh, okay.
So, Mr.
Yes.
There is water in both cylinders. There is water, right?
Once again?
Both cylinders, there is water inside them, right?
So this cylinder is filled with water, and the inner cylinder is immersed in the water.
Okay.
I can try to show you how it goes. Okay, guys, here you are. Okay, here is water. And here is a cylinder. And now we put it into here and then release. Once we release, it goes up the bottle, and we ask what is the acceleration. All right?
Okay.
Just like that.
Well, what is D?
Sorry?
What is D?
B is cross-sectional area of thin bottle.
I mean, you wrote L is much greater than D.
A is slightly bigger than B. They are very close to each other.
In the figure, there is L, and then beside it, the
Sorry?
much greater sign, and then D.
Once again, your question?
In the figure, there is L, and then beside it, much greater than D.
Oh yeah, so this length here from the top of the water level to the bottom of the vessel is distance L capital. So this is much bigger than the diameter of the vessel. So this length is big.
Yeah, Mister,
Yes?
can you check my answer? I don't
Yeah,
have the
this
factor L.
answer looks reasonable. I think it might be correct.
Okay.
Yeah, it might be correct.
Sorry.
Yes?
The cylinder is massless.
Yes.
Can water get inside the inside cylinder? Can it get inside?
Sorry, once again?
Can water get inside the cylinder?
I'm afraid I still didn't understand your question. Please repeat once again. Oh, of course no. This is a cylinder, why it should get? It is here, but this is like I showed you. I showed you how it goes, right? Did you look see how what I showed you? Okay, it's exactly what it happens. Mass of bottle is 0. Yeah, my bottle has mass, but it is also very light bottle. So here you neglect the mass of the bottle. No, Hussein, it is not G. With some, I'm still going to show you once again what I showed you before. Okay, with some, have a look. This is the big cylinder, okay? This is the small cylinder. Now I put this into here, press it down, and now is the initial situation. Now, okay, now you see water level is fairly high now. Okay, now I release it, oops, and goes up. And I ask, what is the acceleration of this bottle here once it goes up? Is it clear now with some? I don't think it's too difficult to understand. Very good. Then I think we had here one guy who was it, Zara, was it? Yeah, Zara, who seems to have gotten a correct result, or close to correct at least. Then I guess I give you one more problem. And the problem is as follows. Here, you know yo-yo. Have you ever had yo-yo?
Yes, yes.
Okay, so the problem is about yo-yo. So we have here a wire going like that, a thread going like that. And then there is in yo-yo, we have a small internal cylinder, and then we have a big outside. Like that, okay? Something like that. Do you agree? It looks
Yes.
it looks something like that. And then the question is, what is acceleration here? When it goes down, what is acceleration? Just this you keep at rest, and this just falls down. Now I think we need to give here certain things. So this is cylinder. This is also cylinder. And a radius, big radius is R capital, and small radius is R small.
Okay. And the acceleration is acceleration for what?
Of the center of mass.
Of the center of mass. Okay.
Yeah. Lama, no, it is not like that. The answer is not correct.
Mr. Can you see?
Sorry? Khalid, no, it's not correct.
Mr. What's by in the last question?
You mean about yo-yo?
Yes.
But Mohammed, you did not solve yet this one, did you?
I tried, but I couldn't.
Oh. Here you need to find acceleration of the center of mass of yo-yo. You have it is cylinder, so you have two big discs and as internal cylinder here. Both are of the same material, and then up the thread here is fixed, and you need to find acceleration of the center of mass.
There is something like pi or so. What is this?
Yo-yo, you know yo-yo, like the toy yo-yo, but which thread wounds around the internal cylinder, and it just goes up and down.
I mean, you draw a line from the center to something like pi, and
So
and
it has internal radius. R capital is a large radius, and R small is a small radius. And
okay, thank you.
Yeah, you're welcome. So shall we do it this problem now together, or you still want some of you still want to try this problem? Tell me now if you still want to try.
Can you give us one more minute?
Okay.
Mister?
Yes.
When I was trying to solve this problem for the UU1, I I don't know, but I had to use the mass of both the small cylinder
Oh,
of
yeah,
radius
you
r
know,
and the bigger mass.
so we assume that these are made of the same material, so the same density. So
Okay.
masses relate to each other as squares of the radii.
Okay.
Yeah. Well, actually, you know, if we take it realistically, I think it is easier if we neglect the mass of the central part, because if you look from side view of the yo-yo, so how it looks, it is like something like that, and then there is the slit here, and then it is side. So this guy here actually has very small mass. I think we can neglect the mass of this middle part, right? Does it make sense? I think it does.
Okay.
It is
I'll
very,
try.
so neglect the mass of the central part. And llama now it is not for a g divided by 3b, no. But some, well, I don't understand, is the YouTube, in the YouTube, is it, what is that, SGX, SGX, X dot, I don't know, I understand Sam, what you're asking. Ah, 2G X dot, this thing here, you mean, this line here? Okay, 2G X dot divided by L plus X dot X double dot equals 0. Now, Zara, I need to think a little bit about the answer what you gave, but I think it's quite possibly is correct. Yeah, it's quite possibly correct. No. How did we get rid of X dot? Because X dot is here and here, so we cancel away. Moment of inertia, cylinder is 1/2 mass radius squared. This was already here on the screen, but cylinder I is 1/2 mass and radius squared. So can we solve it now, this problem, or there are still some of you who are trying to finish it? Still, unfortunately, Lama, it's not GA over B. No, it is not Joshi. So okay, all right. Let us do this problem together. And so now here actually there are two options to which x we take. So we can take whichever coordinate to describe, but here are like two reasonable ways. One is the displacement of this cylinder inside, but the other is the water level. Now actually it appears that the water level is somewhat easier to use. And so let us say that a water level, if this goes up, water level goes down, yeah? So let us say that water levels go down by x. But if water level goes down by x, then this volume here goes somewhere. And the somewhere it goes is here because cylinder goes up. Now this volume here equals to that volume here. And with some, no, it's not correct. And so as a result of this, water is displaced over height L. So from here to here. So that potential energy change now is going to be let us say the mass. Here the mass here is x multiplied by a minus b is cross section. This is volume. X times a minus b is the displaced volume. And we multiply this now by density rho, then we get mass. And if we multiply now by G and L, then we obtain how was the change of potential energy. And this is now negative because it went smaller. And this is on the one hand. On the other hand, the kinetic energy. Kinetic energy, if
Why negative?
sorry?
Why negative? It goes
Because
up.
energy, potential energy goes smaller, potential goes to kinetic. So kinetic goes bigger, potential must go smaller. Mass goes down. It was here and went here.
Okay.
So why did you multiply by L?
This gravitational energy is mass times g times height. Height is it went from here to here.
And why is it times A minus B?
This is how much mass went. So if the height of water changed by x, then the cross-sectional area of this region is A minus B. So I multiply cross-sectional area by height and I get volume. All right. And then we have kinetic energy. Okay, let's see. I used it E times E index P. E, this is potential energy. Now kinetic energy, E sub K. Now, here water is mostly emotionless, so no kinetic energy here. But here water went down, and because like continuity, it must go down by everywhere. So speed of water here is x dot. So it is going to be now x dot squared divided by 2 and multiplied by mass. And mass is A minus B multiplied by L and rho, because this whole column here is in motion. So volume is A minus B times L multiplied by rho, obtain mass. Okay. And then we take derivative and obtain result. Then I take derivative and obtain result. X dot x double dot times A minus B times L and rho minus x dot A minus B rho rho GL equals 0. And now let me switch to black because red is not writing too well now. X dot cancels away. And so A minus B also cancels away. Rho cancels away, rho cancels away, and L cancels away. Only G remains. Only G remains. So X double dot is G. But this is not what we asked. You were asked to find the acceleration of the bottle, but not the water level. Now we have a relationship. If this goes down by x and this goes up by y, the volumes are equal. This volume equal to that. So if this goes up here by y, if this here is y, then we have y times b equals x minus x multiplied by A minus B. So that y double dot equals x double dot multiplied A divided by B minus 1. Okay, equals G multiplied by A divided by B minus 1. Okay, everyone happy?
What is the last answer?
Sorry? Answer is G multiplied by A divided by B minus 1. Yeah, Zara, you had almost correct, but you had divided by A, not B. I think it should be divided by B. Yeah?
Yes, I see.
So you found your mistake?
Yes,
Okay,
thank you.
okay. You're welcome. Now, is this problem clear, everyone? Okay, then we have yo-yo problem, but now we have only 20 minutes left. What shall we do? do you think you can solve it right now for the remaining time, or we'll start doing it slowly together, or what is your opinion?
You can give us some time to think about it.
Okay, I'll give you some time. Now, Zara has done it. I don't know if like it's a little bit difficult to now to give me something else to Zara, because if I give, then it will remain here. Maybe Zara can just go over the old material which we went and prepare for tomorrow's test. Maybe until you'll be back once we just keep close to screen so that you'll notice when I am going to do this together. And yeah, well, now maybe we take a short break and discuss what is going to be tomorrow in test. Tomorrow's test will have 3 problems on kinematics. More or less it's the types of what you had. Projectile motion, then some bars moving find to acceleration, things like that. And yeah, something like taking derivatives, finding acceleration by taking derivatives, something like that. So 3 types of kinematic problems first. And then there is going to be a statics problem, and like talks and such kind of thing, and then there is going to be now what was the one I already forgot. Let me check. What I already prepared the test actually for you. Now. Yes, so there is one problem with friction and like rods and wires and ropes and friction. One is for finding the applying the virtual displacement method to find tension somewhere, and then there is one problem on things what we did today. One problem on that finding acceleration. Now, just because in one problem you might useful to know what happens. Like it's quite easy thing, but 6 problems altogether, 5 hours, 6 questions. Okay, one is rods hinges acceleration. Basically, you need to find acceleration. Second is taking derivatives to find acceleration. Derivatives to find acceleration. Now, third is projectile motion. Projectile motion. Projectile motion threefold. Projectile threefold. Then number 4 is going to be virtual displacement. Displacement. 5 is talk statics. Statics problem with torque balance and things, and 6 is generalized coordinates. Generalized coordinate to find acceleration. Okay. Now, what I wanted you to just to be helpful in one of these problems, let us say that if suppose we have a ball is fixed to a wire, and then this rotates like angular speed omega. And at certain point in time, the break, this rope breaks. Let us say that a rope breaks at the lowest point here. Now at this point here, this rope breaks. How will ball continue moving? If angular speed was here omega and radius was r, so how will start the ball moving if the rope broke at this bottom position? Who can tell me?
It will
Wait,
continue
mister?
horizontally to the left.
Tangent, yeah, Khalid, completely correctly. It will go tangent with speed omega times r, right? It's instantaneous speed here. Is that clear to everyone?
No, mister. Can you repeat, please?
The problem was that if we have ball fixed to a rope and this rotates along the center point, and now suppose this thread breaks when the ball is at the bottom. I was asking how will start the ball continuing moving? And then Khalid answered very fast that we will start continue going tangent. So it means that it will continue moving with the velocity it had at the moment when the thread broke. Thread breaks, and because there is no instantaneous impact, there is no instantaneous big acceleration, it will just continue going with this velocity which it had at that moment when the thread broke. Okay. And now, no kinetic energy. Well, this is a completely different story. I was asking just what is the velocity at the first moment when it starts
Yes,
the break?
the same as the velocity it had before it breaks.
Yeah. So just it continues with the same velocity it had immediately before breaking. Okay. That's all you need to for one of those problems to know. Now,
okay.
And now we have still this problem here. We have something like 15 minutes.
Okay.
And let us do so that I'll give you 10 minutes and then we'll do it together. Is that okay?
Yes.
Okay.
Mister?
Yes.
For this problem that we solved previously, can I show you my solution?
Yes, sure.
Okay, so I just used the volume. I said that the volume that's going to lose from up is going to be replaced in this downward. Since this cylinder has no mass, so there's we can't use it to find the acceleration. So the acceleration of this cylinder is the acceleration of this water, which is downward this cylinder. Yes. So I said that x times a minus b is equal to y times a, and y is the displacement for this like the volume that's gonna lose from upside is going to gain it downward.
Yeah, it's exactly what I did, but I think it's y times b, because if the cylinder goes by y down, so it occupies volume y times b, additional volume y times b, it occupies.
Okay.
Look here on this figure. So this red region here is occupied. It is y times b, not y times a, but y times b.
Because there's already this 2 bars. Okay, I see. Okay.
Meanwhile, what is also a quite interesting problem actually is how what is the acceleration of bubble in water. So if you have water and then you have bubble of certain radius. So here density is very, very small, like 1,000 times smaller than the density of water. So now what do you think, what is the acceleration of the bubble which goes up?
Maybe E something.
If you do it naively, like say that buoyancy force up is mass of the repelled water times G, but then and then divide this by the mass of a bubble, which is basically 0, you get or like infinite or 1000 G, which is not correct, of course. So what is the real acceleration of bubble if you release bubble? And the answer, okay, yeah, it's not so easy to figure out exactly in particular, but it is quite similar to this situation here, that when bubble goes up, so you can think also in terms of generalized coordinates. So if this goes up by x, then the thing is that water around it will also start moving. And so kinetic energy of the bubble itself is negligible, but not that of the water here around. And so it appears that actually kinetic energy, if you do precise calculations here, then kinetic energy is 1/2, and then like effective mass is 2 times smaller. So 1/2 mass of x repelled water x dot square, shows that acceleration A is 2g.
Wait, mister, why is it m/2?
Oh, because it appears it's like this is like more complicated calculations to calculate show that it's if water bubble goes up, the effective mass is half of the repelled water.
So what
Effective mass?
So if this bubble goes up to displaces by x, and then the water is forced to move, it fills the gap like exactly as in here. So this goes up and water goes from here to here. But now, if you make calculations for the water bubble, then if you make precise calculations, then the kinetic energy appears to be 1/2 multiplied by m/2x dot squared, where x is the displacement of the bubble, and m is rho times v, where rho is water density and v is the volume of the bubble. Like this is a result of a precise calculation. It is not easy to calculate, but it is possible to do, and then it appears that it is exactly m/2. And then if you compare this now with potential energy, then potential energy is still just mgx, and so from generalized coordinate method you obtain acceleration is 2g in that case. All right.
M is the mass of what? The water?
M is rho density of water multiplied by the volume of the bubble.
Mister, can you please calculate it like step by step? So I'm curious about how we get m/2.
Oh, once again, this m/2, this is very difficult calculations. This I'm unable to do it so fast. So basically what it means, how to calculate this m/2? It means that we need to know, I need to calculate how exactly water moves around the bubble when bubble goes up. So how you calculate it? So first you study a problem that will go to a frame of reference of bubble, and then water goes around, that goes like streamlines go something like that around it, and then you calculate exactly how velocity depends on the distance. You integrate the kinetic energy of the water then. So the first step is to find how velocity depends on the distance. Second step is to integrate to find the total kinetic energy of the water, and then here is the result.
It seems so complicated.
So the first two
Yes.
steps are fairly complicated, so I definitely it is not something which I can do you here a few minutes, and at level 4 I can show you.
Yes, because the final answer is like 2G. It seems like it's something simple.
Yeah,
Like-
it seems simple, but actually this, to obtain this result, it is not easy at all. Okay, but I think we are running to the position when we need to do it here together, because we have 6 minutes left. And so now suppose this goes down by distance 6. Then potential energy is easy, but kinetic energy is a little bit more difficult. So first we have kinetic energy of the center of mass, which is quite simply mx dot squared divided by 2. And then we need to calculate the kinetic energy in the frame of the center of mass. And then we have just moment of inertia, omega squared divided by 2. And now what is omega? What is the angular speed of this thing? So, so if this goes down by x, so the rope is released by x. Rope is released by x. So this, if this turns by angle phi, then phi times internal radius r is how much rope is released, and this must be equal to x. So omega is phi dot. Phi dot is omega is x dot divided by r. If we take here derivative, we obtain r dot, r is x dot. Okay, and so if we plug this in, then well, this is going to be here. But then I still need I. And what is I? Is 1/2 total mass and total radius squared. And all things together now, E kinetic becomes, okay, this is m small. The total mass was m small, okay? And then kinetic energy is going to be m/2 x dot square. This is what all the terms have. And then here we have 1. And here I has r square, capital square, divided by r small square, because this omega is going to be squared. And that's it. That's all we have. Because mass is already taken care of. X dot squared is taken care of. 1/2 is taken care of. Only r capital square divided by r small squared remains. And then potential energy, of course, is going to be potential energy is of course going to be minus m g x, so that once I take derivative, I obtain m x dot x double dot 1 plus r square divided by r square equals m g x dot, from where now m cancels away, x double dot equals g divided by 1 plus r square divided by r square. Okay.
My answer is different by a factor of 2, but like, okay.
Oh yeah, two. I forgot that two. Sure, that two I forgot. This comes from 1/2 here. Okay, a moment of inertia is 2 here. Okay, and
Okay.
it carries over everywhere. Yeah, sure. Sure, we have that 1/2 because 1, 2 is here. This goes away, but this two here remains. Okay.
Okay. Thank you.
Yeah, you're welcome. Now,
Mr. I have a question. For the day when we had the projectile motion, my connection was not very good, so I didn't attend the full meeting. So, what do you advise me to do?
regarding projectile motion, you mean?
Yes.
So, well, the idea of the projectile motion basically was to the main trick there was to consider free falling frames of reference. So what I can recommend to you, so all these lectures are now in YouTube. You go there and just listen and try doing those things, what we did during the lecture.
Okay, thank you.
Well, we had 2 days of kinematics. You need to just look projectile motion, free falling frames. Just I think you'll be able to find why exactly it was. Maybe let us. I think it was the end of the first day, wasn't it? Do you remember?
What's the statement?
I think we discussed, yeah, the projectile motion. It was the second half of the first day, wasn't it? So you can find this in YouTube, that recording.
Yes, I can. Thank you.
Khalid, okay, Khalid, here the inner disk also rotates. Yeah, inner disk also rotates, but we neglect the mass of the inner disk. They are all connected, and the inner disk is very small compared to the rest, so mass is negligible. So that's why we neglect the mass of the inner disk. Mass and most importantly, moment of inertia of the inner disk. So if we were to take into account the moment of inertia of inner disk, then the expression would be slightly different, but the difference is negligibly small. So so it's okay. Now, shall we finish? So this was now last lecture with us. How you feel about it? Did you learn enough?
Yes, it was different from the other lectures. Like other lectures, we used to solve problems and learn like more and deeply in the concepts. Like with you, Mister, you're teaching us a new ways to solve the problems easier and faster, and I really thank you for that.
Oh, thank you.
Yes, sir, we learned a lot. Hopefully we see you again soon.
Okay, thank you. All right then. Have a good rest tonight and be ready for test tomorrow. And I hope you can do well during the test. And you will be. Yeah, we decided to have it 12 to 5. Yes. Now, just how shall I distribute the test to you? So I could send you also by email, but I don't have all your email addresses. Do you think someone of you can give me all the email addresses so that I can send you by email all the problems? Can someone of you take and collect all the emails and send me by email? Because I do have some, those of you who sent their solutions, but is there someone who volunteers to send me all the emails?
I mean the email. Oh, okay.
So Zara, you can do that.
Ah, yes.
Okay, so yeah. Oh, I already have it. Yeah, very good. So it was now Lama sent. Very good. Thank you very much. I'll just copy paste these emails. Very good. Thank you very much. All right, then good night and good luck for tomorrow. And tomorrow, 5 o'clock, we have session to discuss the problems. So bye-bye. Now, today's lecture to YouTube, it is going to compress something like 1 or 2 hours. And then I'm going to upload, but uploading will also take like maybe 3 or 4 hours or maybe more. So they will be maybe tonight very late, tomorrow morning they will be there. No need to go to Zoom, just everyone solves at home. And once you finish, you scan your solutions. Cam scan, which there is app which makes nice scans of. You can take photo of your solution of the sheet, and then mobile phone and makes it look like scan, and then you send it by email, please. Yeah. So no need to log into Zoom, just take your problem and just start solving. If you have trouble posting the photos, yeah, you can be 30 minutes late, but then we have discussion over here. But anyway, do it as fast as you can. As fast as you can, so that because we have here 5 hours, if you like maybe take a few half an hour or maybe 45 minutes rest here, and then you can. Well, anyway, if you are a little late with your scan, it is okay. Yeah. Yeah, we finish 17, and then you start submitting them. But of course, you should send your solution before you log into Zoom to discuss the problems. So maybe we should start a little bit later, not 17, but maybe 17:15. In that case, you have 15 minutes to make your solutions. Okay, so the discussion will start 17:15. 17:15. Okay, yeah. See you soon. See you soon.